I'm David Shin. This is Lab 3 Circuits for Physics 2212. So the purpose of this lab was to discover how a circuit interacted with different objects, from capacitors to batteries and resistors. We used an experimental model, constructing a circuit in the lab. The system was a circuit, and the surroundings were everything else. For results, the 47 ohm resistor had a potential difference of about 0.87 volts. The 100 ohm resistor was about 1.82 volts. The current is about 18 milliamps. And the charging time was about 1.95 seconds, and the discharging time was about 30 seconds. So some important concepts are, firstly, the node rule, that current in will equal current out. The loop rule, the sum of the potential differences around this closed loop, this closed circuit loop, will always be zero. And Ohm's law, which states that between 2 points, the voltage is equal to the product of the current and the resistance, V equals IR. So here's a lab. Here is an image of our circuit here, as you can see. A lot of the equipment was faulty, which is why every group in our lab section had to work under one circuit, but you can see the battery, you can see the different resistors. And here is the charging portion of the lab. You can see that the light bulb is turning on when the capacitor is charging, but it's slowly dimming, and you see that it dims completely. And so, yeah, the RTA is explaining it right now, but the capacitor is fully charged, the light bulb is fully dim.
If we just disconnect the circuit and try to use the capacitor to power the bulb, we can have
Then you can see that when he plugs the capacitor in, the fully charged capacitor, the light bulb will do the same exact thing that it did when the capacitor was charging. It'll be illuminated, then it'll dim slowly. And so the first part, as you can see in the pictures, was the two batteries, capacitors, and resistors circuit. And the second part was the capacitor, two batteries, and the light bulb, which acts as a resistor. And so here are our calculations for part 1. You can see that the current that we measured was 0.18 amps. And so from those, we can find the theoretical resistances, which we found to be about 100 ohms and 47 ohms. We are slightly above. We found the wire resistances using the measured voltages, and we find those to be 6 and 10 ohms. And the ammeter resistance was 0 as the voltage was 0. And we found that the total voltage from the battery was negative 1.5 volts. And changing the voltmeter to an ammeter led to a much smaller reading on the current, as the voltmeter had a larger resistance than the ammeter. As you can see, that the voltmeter has a higher potential than the ammeter, meaning that the voltmeter will have a higher resistance, as from the Ohm's law. So here's the analysis. You can see that on the 47 ohm, you can see that the potential drops, and then it drops even more across the 100 ohm resistor, and it barely drops across the ammeter. And so the resistance calculated ammeter does not change the current. And the voltmeter has high resistance, as we said before, which means it generates more resistance. And the resistors had a slightly higher resistance from the calculations, which could be attributed to errors from the environment. And the wires also showed higher resistances, which could have affected the calculations as well. You can see that in the graph that it measures that the potential goes up with the battery when it gets charged, and then it goes down proportionally to the strength of the resistors. And so, as I said before, for part 2, the light bulb was illuminated initially when the capacitor was being charged, and then was dimmed as the capacitor was being charged, and also grew dimmer when the battery was disconnected and the capacitor was dumping the rest of its charge. And as I said before, charge time was about 2 seconds, and the discharge time was about 30 seconds. So some sources of error, they could be residual charge or measurement errors in the voltmeter and ammeter. Could have been faulty equipment, as we saw in our lab, that there was only one set of working equipment, and the wires or the resistors could not have retained as much resistance as their theoretical yields were, as they were old. And air and capacitors or other external factors could affect the charge or the current in unpredictable ways. So for the what if, the capacitor would charge much faster if there was no resistance in the circuit at all, as there would be a lack of resistance slowing down the current charging the capacitor. This ideal model would predict a much faster time to charge than our current model, though this prediction is not possible, as it is impossible for any circuit to not have any resistance, as every battery or every wire will have a little bit of resistance no matter how hard you try to make it 0. And the measured time will be different, as the battery or wires in our case had a bit of resistance, which accounted for the longer charge time of our capacitor. Thank you.